We are going to discuss a useful data structure that's called a binary tree. So first, let's ask ourselves, what is a data structure? So a data structure is a way to efficiently organize data. So there are two words here, data and efficiently. Now, what it means can depend on the context, right? So, for example, if you take library cards, it is sort of a data structure where data is books or some information about books, and these cards are efficiently alphabetically organized in the librarian computer or like cardboard boxes or anything similar to that. You can think about mailboxes. It is sort of a data structure because you have apartments in the building, there are mailboxes that are organized the same ways as apartments in the building, so you can efficiently find where to put a letter for anyone. You can think about the whole street system of a city as a data structure because there are streets, there are numbers, and you can efficiently find a house you want because you know a street and a number. Of course, efficiently means different things in different contexts. So, for example, if we talk about the city, having different streets and not everything is a street, not every street has the same number of houses and so on. All of this is not super efficient, but historically we have to deal with this. Well, so the problem like this exists much less in like abstract computer science, and I think binary tree is a very cool example of a very basic, very simple data structure, but that demonstrates everything that is actually cool about having data structures. So let's dive right into it. So what is a binary tree? Think of a following image. So we have nodes, and each node has children. This is a left child, this is a right child. Now, every child can also have children. So here, you may have noticed that the very first node, which by the way is called a root of the tree, I made two children. This is not necessary. In fact, for the binary tree, every node can have 0, 1, or 2 children. So, for example, this is a tree. This is a binary tree. This is a binary tree as well. Here is the root, and it only has one child. This is a binary tree. This is a binary tree. Even something like that, tak, 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 is still a binary tree. Indeed, here we have a root, and we have right child, right child, right child, right child, and all of this is not present. So let us discuss a very concrete thing about binary trees right away, which is how to implement a binary tree in Python. So basically, how to turn abstract into concrete is the key capability that you need to possess to efficiently solve LeetCode and other problems about data structures and algorithms. But this is a base, right? We need to understand how to take this abstract concept that we just discussed, that there are nodes, nodes have children, there could be 0, 1, or 2 children, and how do we convert it into real code, right? So to understand how to implement it, let us notice one thing about binary trees. So the key element of a binary tree is a node. So if you take a look, for example, here, all of this is a node plus left child that is not present and the right child that is not present. If you take a look at, let's say, this piece, this is also a node, this node, with only the left child present. If you take a look at our very first, let me draw here, it will be nicer. If you take a look at this example, same, we have a node, and there is a left child and a right child. So basically the question is, how do we efficiently express this concept in Python or in any other programming language, but I will stick to Python for this. So, well, let's just create a class for node. We'll have class node. And this class will have two fields. Left child, which is also a node, and right child, which is also a node. So now pause for a second and think about the following thing. Did I capture everything? This is a very important question for, well, turning abstract things into concrete. Did I provide necessary amount of information to make this useful? So think about this for a second, and while you're thinking, I'll talk about a slightly different concept here. So left and right, these two are nodes. This is also a node. This should not bother you, right? This is like classic recursion. And what I want you to understand that this is totally normal. Yes, we have a class node, and we have two fields left and right, which are also nodes. So now, if you take a look at the binary trees, we said that we don't need to have two children, right? So if you take a look at this class with this typing, we assume that every time the node is present, right? This is not great because we need 0 or 1. So how do we do it? Well, let's store none instead of missing nodes. So here in this example, it will turn nodes into optional of nodes. So basically, every time we have nodes, left and right can be either none, which means that the child is missing, like here. This is none, or it can be another node with some children of its own. So when we initialize this class, an object of this class, we can write something like root is equal to node, where left is something and the right is something. So for example, if you want, so the question here is how do we, well, make a tree, right? Because we need to populate this with some data to solve some problems about it, right? So basically the way to do it is, let's understand how to create just an empty, well, not an empty node, but a node which is just like this sort of a blob without children. Sorry. So we will create this the following way. We'll say, let's call it element equals to node of none and none. So using these elements, you can create your tree, you can create like other roots, you can populate these roots with elements. Note that when your tree is complete, you only need to store the root, because everything else will be accessible through the children of the root. Now, let's get back to the question. Did I define everything? No, in fact, I missed a very important fact that, well, when we have a data structure, we need to have data in it, right? So we need to organize some data. This now only stores some sort of tree-like structure that is not useful on its own, right? So we need to put something else in it, which I will call data. And this data will be of whatever type you want. So you can create an integer tree, for example, or you can create a tree that consists of some like weird blobs. You can even create a tree where data is trees itself, like no problem about that. Depends on your problem, on what you need to solve. Now, so we discussed how to implement the binary tree in Python. Now the question is, what can we do with trees? And why am I interested in what we can do with trees? Because this answers the question of efficiency, right? We are saying, okay, putting numbers in this some sort of tree-like structure is going to significantly improve our lives. So how? That's the question that we are going to answer now. So what we can do with trees is, given a root, let's say we have a root. We can access children of the root, right? So when we have a root, let's have our Python snippet. When we have a root, which we defined before, we can say root.left, and therefore access the left child of root. We can say root.right, and we can do it indefinitely. We can do it in a loop. We can access, because this is also node, we can access it. We can do anything we want with it. So we can do something like root, left, right, and define a path this way. So root, left, right is going to be this node, for example. Now, I will give a very practical example of how organizing, let's say, numbers in a structure like this can help us build things more efficiently. Now, imagine that a tree contains integers, let's say 10, 7, 141, 3, 9, say 90, and 150. So maybe you notice something, an interesting property of this tree that I defined, which is for every node, the left element is smaller than the node element, and the node element is smaller than the right element. So 7 is smaller than 10, 10 is smaller than 131. Why is it important? Well, it is basically a binary search tree, right? Because what we can do is, let's say we are searching for 90. We are searching for 90, so we go to the root. We compare 10 and 90. 90 is bigger than 10, and we know that everything in the left subtree is smaller than 10. So we only need to go to the right subtree. We are not interested in all this bunch of numbers over here. So we go to the right subtree, looking for 90. 131 is bigger than 90, so we know that compared to 131, 90 can only be in the left subtree. So we go here, we see 90, well, we found 90. Now, this is a very tough example because, it's doesn't sound like a very, production task to find integers in a tree like this, but this can have a much more practical meaning. Like, imagine users in a database, you need to find someone's birthday today, things like that. So, for example, you have users organized in who has a birthday today, and you want your system to find out everyone who has birthday today. And for this, it may be pretty useful to have some sort of structure like this. In reality, all of this is hidden behind the databases. Like, in reality, you never ever need to do something like that. At the same time, it's useful to know how to do it, right? So this gives us a very interesting complexity thing to think about. So in this two example, I said we don't need to look at all the data, we only need to make a few steps. So the question is, how many steps? So imagine we have n elements in the tree, and the binary tree is full. Full means that almost every element has two children. The only nodes that are not allowed to not have two children are some of the nodes on the very last layer of the tree. For simplicity, because we only care, so asymptotically we only care about very big numbers, so for simplicity we can say the tree is full, so every element has two children with the exception of the last layer that has 0 children. So the question is, what is the height of the tree? And depend if we have n elements in the tree. So, well, how to compute it? Imagine, like, let's do it vice versa. Imagine that the height of that tree is h. So how many elements we have on each layer? On the first layer we have 1 element. On the second layer we have 1 multiplied by 2 elements, because from the tree we have 2 elements. On the third layer, we have 1 multiplied by 2 elements, because out of each 2 elements here, we grow 2 elements here. So on the level h, we have 2 to the power of h elements. So if you inverse it, we find out that h equals logarithm of n. This is super important. This is super important for our complexity estimations, because from now on, we know if we have a binary tree involved and our algorithm, our operation, anything, needs to traverse the tree in the way of we go from a root, we either take left or right, and we have some sort of finding out what we meet, checking some condition on the way, or doing some operation that requires some amount of like other operations that require some asymptotic, right? This will take us logarithmic complexity. So, for example, for this two example of searching for a number in the root, this search is done in O of logarithm. So I scribbled out the little 2 in here, because as we know, for estimating complexity, constants do not matter. So logarithm, it doesn't matter if it's what base of the logarithm we're using, because all logarithm are different by constant. All right, so that's it with what trees mean for estimating the algorithmic complexity. Now, by itself, binary tree is not extremely interesting. It becomes interesting when it is used in other algorithms that massage the data the way that it ends up being a binary tree. So let's consider a little toy example that may be useful for LeetCode, which is how to sum up nodes in the tree. Okay, what do I mean? So once again, we have a tree, and there are some numbers: 1, 3, 7, 8. This is not a binary search tree. I'm not introducing any limitations on it. It's just a binary tree. And I want to sum up all these numbers. So find out 1 plus 1 plus 3 plus 2 plus 7 plus 8 plus 100 plus 90. This is basically an exercise in traversing the tree. So what do we need is we need to visit every single node of the tree, and we are given the root. So how do you do it? The approach for solving anything with tree-like recursion is, first, you need to define exit condition. By the way, all of this applies to recursion as well. So it's like how to think about recursive problems in general. So exit condition. How do you understand that you reached the edge of the tree, right? Let's check it right away. How do we understand? Well, both children are known, right? Because if both children are known, this is a leaf. By the way, this is called a leaf. This is a leaf and you can quit. So let's check. If root left is known and root right is known. So in this method that I call traverse, we actually want to compute the sum, right? So I called it traverse to make it a little bit more generic, but we'll do a simple thing and compute the sum. So what is the sum of a tree that consists of one node? So if we take a look of just this little subtree, well, obviously just the value of the node. So if we know that our tree is limited to this one element, then the answer for this is just root dot data. Now, an important thing, you can see that I call this one root. I could have called it a node, but in general, here, this function will traverse everything down from a given node. For example, if we call this traverse function from this subtree, it will traverse this subtree and return a sum. So we define the exit condition. Now we need to define how to combine left and right. How to combine left and right? Well, imagine we have this tree and there is a left subtree and right subtree. Well, obviously the sum of the whole tree is the sum of left subtree, the value in the node, and the right subtree. Well, let's write this out. If you are screaming now, you are right, because this contains a pretty big mistake. What is this pretty big mistake? This pretty big mistake is that we assume that all nodes either have 2 children or 0 children, because we process the condition where we have 0 children. This is when we have 2 children. What happens if you have just one child, right? Like here. So what happens is we call traverse of known, and this will raise an error right here because known doesn't have attribute left. So how to tackle this differently? Basically, we can have 2 ways to do it. The first way is we assume that root can be known by itself and the sum of known is 0. So root can be optional of node. We can say if root is known, return 0. This is one way to solve it. The other way to solve it is to check that root left and the root right are not known and do things accordingly, right? So we first find out sum left, then we find out sum right, and then we sum everything up. So most of simple and even medium exercises on LeetCode for binary tree should be solved using these techniques. So let me know if you have any questions and let me know what you think.